Okay, welcome to another Orbiter 2010 video, and this video is going to be another installment in the video series that I'm putting together that has a particular emphasis on people who are brand new to Orbiter. You've downloaded the program, you have it installed and working, but you don't really know how to get around the program very well. Now, I am assuming that you are watching these beginner guides in order. The last video, we took a look at how to not only take off from the runway and get into orbit, but also how to start thinking about how to arrive in orbit so that we would be already in plane with a particular target object. And in this case, our target object is the ISS, the International Space Station. Now, in that last video, once we arrived in orbit, we were a little bit out of plane. We were 0.66 degrees out of plane with the ISS. So I went ahead and showed what we would need to do in order to resolve that last little bit of difference in our inclination. But it may not be completely clear as to exactly what's going on with all this plane alignment stuff. So I want to spend at least one more video going over a bit more detail about how all this plane alignment stuff works. Now, when we arrived in orbit, we'd taken off from KSC, and we crossed over the ascending node, and we took care of the little bit of plane difference that we had. And you might wonder, well, what would happen if we had not done that plane alignment burn at the ascending node? What if we forgot, or what if we accelerated time forward and accidentally passed over the ascending node and we missed our opportunity to do that plane alignment? Would it be the case then that we would just have to exit orbiter, start back over on the runway, and basically do everything all over again? Is there only one particular sequence of events that allows us to complete our mission? And the reason I bring this up is because I actually was under that impression to some extent myself 3 years ago when I was brand new to Orbiter. I was used to reading instructions from other people, forum posts or tutorials or guides, and they were written, sequentially. Do this, then do this, then do this, and it makes sense to write things that way. But you're left with the bit of uncertainty when you follow directions sequentially. If you miss something, then you always feel like, well, I gotta start over. So what I want to show here with regards to the aligned plane, if the sequence doesn't go perfectly, it doesn't mean that you're unable to rendezvous with the ISS. So in this example, we have actually missed the ascending node for some reason. We don't know why. We forgot about it, or we were warping time forward and we just went forward too far. Whatever the case, we missed the opportunity to align the plane at the ascending node, and we're now over here, and you can see we're still out of plane. Now, what I want to do is take a look at the outside view using a particular add-on that allows us to look at our orbit lines all the way around the Earth. This is very convenient for illustrative purposes. So this will help explain why we don't necessarily have to do our aligned plane maneuver right away. So I'm trying to just find a good camera angle here, and that's pretty good right there. We can see this blue line down on the bottom. That is actually the orbit of the ISS around the Earth. And this green line is the orbit of our Delta glider around the Earth. And if we look at this side-on view, you'll notice that the Delta glider is kind of up here, and the ISS is down there. There's a bit of a gap. So that is the difference in our plane, that we're just a little bit off. We're not too far off, but we're off enough that we wouldn't really be able to rendezvous with the ISS very easily. Now, if we kind of come back inside and we warp time forward, and we're going to go forward a lot. We're going to skip the descending node because I just want to show a point here. As we go around the Earth, let me kind of come outside. Let me find a camera angle that works. I guess that will work. Sometimes it can be tricky to find good camera angles with Orbiter, at least ones that behave how you want them to behave. Okay, we're just going to go inside, and you can see we missed the descending node. And we're going to come around here, and we're going to skip the ascending node as well. And all I really am trying to paint a picture of is the fact that our relative inclination is not changing. So you might get the idea that if you miss your opportunity to do your plane alignment burn, then maybe you're ruining the flight because your relative inclination is going to get so bad at some point that you're never going to be able to get into alignment with the target object. So you can see here that's not the case. Even though we missed the ascending node now twice or 3 times, and we've missed the descending node a couple of times, our relative inclination never changes. And that has a lot to do with the fact that we are in a stable low Earth orbit. That is, our periapsis and our apoapsis are high up enough above the surface that we're not getting any drag through the atmosphere that would be impacting our altitude or would somehow be impacting our relative inclination. Okay, so let's go back to real time here. And we look outside again, and if we just kind of look at that, those side-on views, we can see there's no change in our orbit plane. It's really, it's the same. Of course, this time we're looking at the other side of the Earth, so the Delta Glider from this vantage point is up on top. Now let me do one more thing. I'm going to exit out of this scenario because that orbit line isn't real obvious in that particular scenario. So let me load one more. Take a sip of water while that's loading. Now in this scenario, what I've done was I made a copy of the previous one, and I exaggerated the relative inclination by, almost 10 times. So in this scenario, we're saying that we've arrived in orbit and we're somehow 5.41 degrees out of plane, which certainly can happen if you're not, more careful with your ascent up through the atmosphere. But let's take a look at the orbit lines with this greater inclination, because it'll help show the difference. Here you can see, much more obviously just how far out of plane we are. Again, the green line is the orbit of the Delta Glider, and the blue line is the orbit of the ISS. So you can see with the 5-degree inclination, or 5.5, close to 5.5, you can see just what exactly is happening here, what the problem is with our orbit. We cross over at that point, and we cross over on the other side of the Earth, but we're, quite a bit, out of alignment with the other vessel. So I just wanted to show that, these orbit lines, because it really helps you visualize what orbit, what the orbital plane means exactly. So let's just briefly, before we leave this scenario, let's align the plane so we can see the difference. So we'll come around here to the descending node. And as we approach the descending node, remember, there's a particular orientation that we need to be in if we're going to successfully align the plane. And try to remember back to the previous video what I was saying about the ascending node and the descending node. How do we know what orientation we need to be in for the descending node? The memory trick that I use, I'll go through it again briefly, is AN equals AN. ascending node equals anti-normal, and therefore the descending node is just the other one. So in this case, ascending node is anti-normal, that's that one. So we're over here, we need the other one. So as we're coming up to the descending node, we're getting close enough now, we'll go ahead and press normal plus so that we can get oriented correctly. And how do we know when to do the burn? This number here is the amount of estimated thrust that we need, and it's telling us that we need 56.25 seconds using the full power of the main engines in order to bring this relative inclination down to 0. And since our burns need to be balanced, remember I talked about balance in the previous video, how we need to do half our burn on one side and half on the other. So that means when the time to the node is half of this number, that's when we need to begin our burn. Now I'm going to go ahead and use the full power of the main engines in this particular example because I want to be able to show the aligned plane. Or I want to be able to show those orbit lines from the external view. So before I get to that point, let me make sure I have a good camera angle. That'll be good. Now I'm just going to warp time forward until I'm at about, I guess that'll be 26 seconds maybe, something like that. Half of 56. So we're just waiting for the timed node to be half of that number. And as we get close, we'll come back to real time. Now we'll just wait for it. Press plus and hold it. Now I just want to look at the external view so you can watch exactly what's happening with this orbit line stuff. And you'll notice that this green line gets ever closer to the blue line and will eventually be exactly matched up, and that means that we are in plane. So that will give you a very good visualization of what's happening when we align our plane. Quick look inside. You can see we're down to 2.5 degrees now, and this is getting closer. Let's go back inside because we're almost there. Down to 1 degree, and then we'll cancel it, or we'll kill the main engine here when it gets down to 0. And we'll kill the main engine now so we don't overshoot. And then I'll just apply a little bit more. And there we go, we're down to 0.00. Now let's look at our orbit line. And you can see now that kind of no matter how I tilt the camera, the Delta glider and the ISS lines are indistinguishable from a side view. Now we do have a difference in altitude. You can see that the Delta glider is closer into the Earth, and that's because we're orbiting at 200 kilometers and the ISS is out, more like closer to 400 kilometers. And if we sort of do a top-down view, that might actually give us a better look at the altitude. Okay, so that is that for orbit lines. That's about everything I wanted to show. But there's still a little bit more to discuss with a line plane before we totally abandon this topic. Now I'm going to leave this version of Orbiter and start the one that uses the direct the D3, D9 client, and I won't try to explain that. So let's load up a different scenario. And once this one's loaded, we'll have a look at basically where the Delta glider was previously, which is down to a 0.00 relative inclination. So let's load up this Delta glider, which is a copy of that first one, but it's placed into a slightly different orbit. And let's just do a little bit of maintenance here. Let's turn orbit lines to orbit plane, and let's target the ISS over here. Now, let's fix this little bit of relative inclination difference, quite a bit of relative inclination difference that we have. But I want to show a little bit of a problem that you can run into if you use the full power of the main engines. So we've passed the ascending node. That means we're coming around to the descending node, and that will be our next opportunity to align the plane. So let's go ahead and warp time forward to get closer to that point. And as we discussed before, according to this MFD, we need 35 seconds using the full power of the main engine. So we're going to balance the burn half and half. That means when the time to the node is about 16 and a half, 17 seconds, that's when we'll do the burn. Getting close to that point, so we're going to come back to real time, and we're not anti-normal, so we want to go orbit plus. Now I want to bring up orbit MFD on this side, and we're going to do this burn using the full power of the main engines, and I want you to watch as we do that for 35 seconds. It's going to have an impact on our periapsis and apoapsis. It won't be massive, but it will be enough that we want to make mention of it. And it's actually worse in other vessels. The standard Delta Glider autopilot for orbit plus and orbit minus is pretty good, but if you use a different vessel like the XR2 Ravenstar, it uses the same autopilot as the Delta Glider for these orientations, and it's not balanced quite right. So if you use the full power of the main engines on the Ravenstar to do these types of burns, it has more of an impact on your periapsis and apoapsis. And that's kind of why I want to show this point. So let's get over to the time when we need to begin our plane alignment. We're really close. So let's go back to real time. Okay, now we're burning, and again, we're using the full power of the main engines. Relative inclination's coming down. That looks good, but notice what's happening over here. Notice that even though this autopilot's very well balanced, it's still having an effect on our apoapsis and some smaller impact on our periapsis. And that's not really what we want. When we've got a circular orbit, we want to keep it circular. So go ahead and kill the engines here when it gets down to 0. And I accidentally overshot that a little bit, and that's actually another issue that you can run into when you're using those full power of the main engines. It's really easy to overshoot.
Translation.
And then you have to undo some of what you did. Here I'm just using a little bit of reverse translation to eliminate some of that thrust. You can see down here it's counting down, and that fixes my relative inclination. But we don't want to overshoot. It's a waste of fuel and it's just sloppy. But you can see by doing it that way, it changed my orbit, and it's actually okay. I mean, it's only, my eccentricity is only 0.0007 now, but again, it's not what we want. That's not a desirable way to do the burn, especially when you can avoid it, and especially when you are using other crafts that don't have the autopilot balanced quite as well. So let's pick a different vessel. I want to show also, let's target the ISS here, and you're going to see that we're way out of plane. So what happened in this case? Well, this was a case where we took off from KSC, and instead of banking the vessel to the proper heading and taking off and getting into orbit and trying to keep our plane aligned while going up through the atmosphere. In this case, what I did was I just took off and I went in a 90-degree heading and I got up into orbit without even looking at the aligned plane MFD. I just simply went to 90 degrees and kept my heading in that direction. And you can still align the plane after you get into orbit, but one thing that you kind of want to equate in your mind is that plane change equals expensive. When you're in a circular orbit like I am now, and you're close to a mass, a massive body like the Earth, which is, relatively speaking, it's quite massive, this plane change maneuver is very costly in terms of how much fuel you're going to use. But you can, in fact, get the vessel into plane, but it may take multiple burns to do it. And that was one thing I wanted to show in this example. So if for some reason you take off and just go to a heading of 90 degrees, you are way out of plane with the ISS when you get into orbit, which we can see here. Let's go orbit, plane, and then target the ISS. You can see just how far off we are, but we can actually resolve it. And with a vessel like the Delta Glider, which has just tons and tons and tons of extra fuel, then it just becomes a matter of doing your burns at the proper time. And that wouldn't be any different than if the relative inclination were very low, like 0.5. We would just come around to the descending node, noting that our burn is much longer, so we don't want to get very close. We need to start this burn when we're all the way down to about 200 seconds from the time to node, so we need to plan on doing this burn much earlier. So we'll go to orbit plus. I'll use a little bit of 10x to let the autopilot settle. And I'll continue warping time forward until the autopilot tells me to do the burn. And we'll take a look also again at the orbit MFD so we can see how much more of an impact it has on our altitudes when we do a burn of this magnitude. Because this is going to be a very long burn, 400 seconds. I mean, if you divide that by 60, that's over 5 minutes. This is a 5-minute, 6-minute burn, a little over 6 minutes. But there are two things to note here. The first one is the size of the burn and the impact that it's going to have on our altitude if we use the full power of the main engines. And the second thing is that when your burn gets to be a certain size, you usually can't complete the whole burn in one passage. Getting very close. Okay, full power of the main. And I'm actually going to go to 10x just due to the amount of time that this burn will take. Notice the impact that it's having on our altitude. And we'll get as much of the burn done as we can on this passage of the node, and then we'll go around to the other node to finish off the burn. So that's something I want to show, is that you can split the burn up into multiple parts. Okay, let's go back to real time because the MFD is going to tell us to disengage the engines here pretty quickly. And look at this. I mean, we've raised our orbit on the other side by 200 kilometers. That's how bad things can get if you have to do this for a long time. And this could have been avoided by using less thrust, but it would take longer to do the burn, obviously. Okay, so the MFD is telling us to quit. And notice that we've still not got our relative inclination all the way down to 0. So we have to go around to this node to finish it off. And don't forget that since we're going to a different node, we need a different orientation. Okay, we're getting close to that point. Okay, so we'll go orbit minus. And notice now we've only got a 2-second burn left, so this will be very quick. Okay, that takes care of that. And now we are in plane with the ISS. If we look here on map MFD, you can see there that the lines match up. And if we want to be
rotation, translation,
very picky about it, we should fix that last little bit, because I accidentally overshot. There we go. Okay, so that is basically everything that you need to know about getting, doing the aligned plane maneuver from a circular orbit. And I actually kind of want to emphasize that point, that these are circular orbits that we're using, because there's still more to know about a line plane when you're not in a circular orbit. There's one last thing I want to talk about before we leave this completely. And that is if we're using a different vessel. In this scenario, I've made a copy of the situation that we had with the Delta glider, where it was 3.41 degrees out of plane, but this time we're in the space shuttle instead of the Delta glider. Now this is an important thing to note, because the power of the OMS engines on the space shuttle are, they're about as powerful as the RCS thrusters on the standard Delta glider. So in other words, they're very weak. These engines don't have much thrust at all. Notice that the aligned plane MFD says that we need a 1,000 second, almost 1,100 second burn to bring the relative inclination from 3.41 down to 0. And I don't even think that there is that much delta V in the OMS engines. I'm not sure. But we've missed our opportunity to do the burn here at the descending node. You can see it's telling us to thrust normal, and we're not in the proper position. So I'm just going to warp time forward to go to the other node. And we can see again that we need to begin the burn when we're 500 seconds from the time to the node, because we're taking about half of that number. So we're going to begin the burn much earlier than we would in the Delta glider. And this is why it's so important to arrive in orbit with the relative inclination that's down, to just 0.2 or 0.3 or something very low. Because when you're using vessels that are reasonably realistic, well, totally realistic, I mean, the space shuttle, it doesn't get any more realistic than that. But when you're using vehicles that are more realistic, you simply can't afford to be very far out of plane. So we're coming up to the ascending node. Let's go anti-normal. And even maneuvering the space shuttle takes a lot longer than maneuvering the Delta glider. Now, I was thinking I'd probably avoid this, but I'm going to go ahead and discuss it anyway. The space shuttle is actually, the OMS engines are 15 degrees out of alignment with the center position. So technically you can't use the autopilot to do a plane alignment burn because it just won't work very well. You notice there's this crosshair down here, and this crosshair is actually telling us where the proper alignment is for the OMS engines. So as we're coming up to the time to begin the burn, what we actually want to do, I'll show here in a moment. Let's go forward a little faster. What we actually need to do is turn off the autopilot, and we need to rotate the vessel so that this green crosshair is on that 90-degree position. So this actually makes using the space shuttle quite a bit more difficult because you can't just use the autopilot. So there we're pretty well lined up. So now we're just waiting for the MFD to tell us when to begin the burn. And there it is. So I press plus and hold it, and then control to lock the engines. And you can see how much slower this is coming down, how much slower the relative inclination is coming down. So there's a huge difference between this vessel and the Delta glider in terms of performance. So that's why anybody that is just starting out with Orbiter, you definitely want to use the Delta glider for quite some time, because doing these types of maneuvers with a craft that's more realistic is very difficult. And again, this will take 1,000 seconds, so that's like, close to 20 minutes just to do this plane alignment maneuver. And obviously I'm not going to sit here and let that complete because that's just way too long. But I just wanted to show just how important it is to plan your launches so that your relative inclination is low when you arrive in orbit. I mean, imagine if you took off with the space shuttle and you arrived in orbit with that 47 degrees out of plane like we showed with the Delta glider when you went to the heading of 90 degrees. Obviously you would never be able to get the plane aligned without using all kinds of fuel cheating. Okay, so let me kill the main engines. In fact, here it is. Yeah, I did make a copy of that. So if we target the ISS here in the shuttle, this is the scenario where we're saying the space shuttle took off and it went to a heading of 90 degrees and it arrived in orbit 47 degrees out of plane with the ISS. And according to the aligned plane MFD, we would need 15,000 seconds of burn time just to align the plane. That is absolutely ridiculous. Okay, so that is going to be it for this video. Hopefully now you know everything that you need to know about the basics of getting into alignment with another target body. In this case, it was always the ISS. But this concept applies even if you're wanting to rendezvous with a different object, like maybe Mir, or if you're wanting to rendezvous, with another vessel, or even if you're around the moon and you want to rendezvous with the lunar space station instead of the ISS. This concept is the same no matter which body you're orbiting. Okay, so just trying to think if there's anything else I want to discuss before ending this, and I don't think that there is. So if you like this video, go ahead and leave a comment down below, and I will see you next time. Okay, welcome to another Orbiter 2010 video, and this video is going to be another installment in the video series that I'm putting together that has a particular emphasis on people who are brand new to Orbiter. You've downloaded the program, you have it installed and working, but you don't really know how to get around the program very well. Now, I am assuming that you are watching these beginner guides in order. The last video, we took a look at how to not only take off from the runway and get into orbit, but also how to start thinking about how to arrive in orbit so that we would be already in plane with a particular target object. And in this case, our target object is the ISS, the International. Instructions from other people, forum posts or tutorials or guides, and they were written, sequentially. Do this, then do this, then do this, and it makes sense to write things that way. But you're left with the bit of uncertainty when you follow directions sequentially. If you miss something, then you always feel like, well, I got to start over. So what I want to show here, with regards to the aligned plane, if the sequence doesn't go perfectly, it doesn't mean that you're unable to rendezvous with the ISS. So in this example, we have actually missed the ascending node for some reason. We don't know why. We forgot about it, or we were warping time forward and we just went forward too far. Whatever the case, we missed the opportunity at the International Space Station. Now, in that last video, once we arrived in orbit, we were a little bit out of plane. We were 0.66 degrees out of plane with the ISS. So I went ahead and showed what we would need to do in order to resolve that last little bit of difference in our inclination. But it may not be completely clear as to exactly what's going on with all this plane alignment stuff. So I want to spend at least one more video going over a bit more detail about how all this plane alignment stuff works. Now, when we arrived in orbit, we'd taken off from KSC, and we crossed over the ascending node, and we took care of the little bit of plane difference that we had. And you might wonder, well, what would happen if we had not done that plane alignment burn at the ascending node? What if we forgot, or what if we accelerated time forward and accidentally passed over the ascending node and we missed our opportunity to do that plane alignment? Would it be the case then that we would just have to exit orbiter, start back over on the runway, and basically do everything all over again? Is there only one particular sequence of events that allows us to complete our mission? And the reason I bring this up is because I actually was under that impression to some extent myself 3 years ago when I was brand new to orbiter. I was used to reading to align the plane at the ascending node, and we're now over here, and you can see we're still out of plane. Now, what I want to do is take a look at the outside view using a particular add-on that allows us to look at our orbit lines all the way around the Earth. This is very convenient for illustrative purposes. So this will help explain why we don't necessarily have to do our aligned plane maneuver right away. So I'm trying to just find a good camera angle here, and that's pretty good right there. We can see this blue line down on the bottom. That is actually the orbit of the ISS around the Earth. And this green line is the orbit of our